I'm R. Prabha, Assistant Professor in the Department of EC, SNS College of Technology. In this video, we are going to see the topic binomial array and pattern multiplication for the course transmission lines and antennas. So, a uniform distribution in an antenna yields the maximum directivity, and the minor lobes are relatively large. The amplitude of first minor lobe is 24% of major lobe maximum. In some applications, what is required is the minor lobe must be undesirably large. So, for that, the pattern has a power beam width of 23 degree, but the side lobes are radiatively large. So, because of this reason, we are going for binomial array, because in the previous case of uniform array, the beam width is lower, but the but there are more side lobes. So the side lobes are unnecessary, and it yields to power reduction in some applications. So here the binomial array is the case of arrays of non-uniform amplitudes as per the demand of modern communication, where narrow beam, that is no minor lobes, is preferred. So it is the greatest need to design an array of only main lobes. The ratio of power density of main lobe to power density of the longest minor lobe is termed side lobe ratio. So a particular technique used to reduce side lobe level is called tapering. So in the binomial array, since currents and amplitude in the source of linear array is non-uniform, and it is found that minor lobes can be eliminated if the center element radiates more strongly than the other sources. Therefore, tapering need to be done from the center to end radiators of same specifications. Binomial array is a common example of tapering scheme, and it is an array of n-isotropic sources of non-equal amplitudes. To reduce the side lobe level, John Stone proposed that sources have amplitudes proportional to the coefficients of the binomial series 1 plus x the whole power n is equal to 1 plus n minus 1 into x plus n into n minus 1 into n minus 2 by 2 factorial into x cube plus n minus 1, n minus 2, n minus 3 by 3 factorial x cube, and so on. So here n is the number of radiating sources in the array. So we can simply calculate the amplitude of each element in a binomial array by using Pascal's triangle. So in the Pascal's triangle, for example, if we have an antenna array of 1 to 10 radiating sources, if n equal to 1, according to Pascal's triangle, its amplitude is 1. For n equal to 2, the amplitude ratio is 1:1, and n equal to 3, it is 1:1, n equal to 4, it is 1:3:1, n is equal to 5, 1:4:6:4:1, and so on. So here if we observe this Pascal's triangle, all the end elements are having the one time the amplitude ratio, but the middle element is the sum of the previous row adjacent elements. And the uniform array versus binomial array comparison. For uniform array, we have a beam width of half power beam width of 23 degrees, whereas in binomial array we have 31 degree. So but the advantage in this case is there are no side lobes in binomial array, but in the normal case of uniform array we have side lobes, and half power beam width is a minimum in case of uniform array, but in binomial array the half power beam width is higher. So what happens is, if half power beam width is higher, the directivity reduces, because the directivity and beam width is inversely proportional. If directivity decreases, it will lead to the less sharper radiation. So at the cost of the directivity, we are eliminating the minor lobes. So the disadvantages of binomial array, as we discussed, half power beamwidth increases, hence the directivity decreases, and another disadvantage, if the array length increases, larger current amplitude ratio are required. So next we are going to see another method of calculating or sketching the radiation pattern in a speeder way is called pattern multiplication. So this method is very useful in the design of arrays because it makes possible to draw the patterns of complicated arrays very rapidly, almost by inspection. So according to pattern multiplication, the total field pattern of an array of non-isotropic but similar point sources is the multiplication of individual source patterns and the pattern of an array of isotropic point sources, each located at the phase center of the individual source and having same relative amplitude and phase. The total phase pattern is the addition of phase patterns of the individual sources and the array of isotropic point sources. So we have for an example 4 isotropic element array. It is a linear array because all the elements are kept in equal space. So the distance between the two adjacent antennas are taken as d. So the total distance d plus d plus d, that is 3d by 2. 3d. So here the distance between the two antennas is taken as d is equal to lambda by 2. Its radiation pattern is consists of 4 lobes. And according to pattern multiplication method, for finding the individual pattern, we have to find the radiation pattern due to the antennas 1 and 2. So we know that for two antennas having the equal amplitude and equal phase separated by lambda by 2 distance, the radiation pattern is 8-shaped pattern, and this is the case of unit pattern. And for getting the unit, it is group pattern, the total distance is added. It is considered as lambda by 4 plus lambda by 2. So totally the distance between all the antennas is lambda. So what happens is we are considering antenna 1 and 2 as one unit and antenna 3 and 4 as another unit. So the antenna 1 and 2 is considered as the one unit and it is kept in the middle of the midway between antenna 1 and 2, and antenna 3 and 4 is considered as the another unit and kept in the midway between 3 by 4. Now the distance is calculated and it is lambda. So now we have to check the radiation pattern of the group antenna, that is antenna 1 dash and 2 dash. So here the radiation pattern is 4 lobes. So the resultant pattern is the common area, and we have the common area is the 8-shaped area, and since we have here we have the 4 minor lobes. So similarly we can calculate the linear array of 8 isotropic elements. Here also we have to find out the two patterns, unit pattern and group pattern. For getting unit pattern, we have to check the 4 antennas are kept in free space, and we have already calculated the case 1 8 shape. And for getting group pattern, the 4 antenna elements, first 4 antenna elements are considered as one group and kept in the middle, that is in between antenna 2 and 3. And similarly the antennas 5 6 7 8 are considered as another unit and it is kept in the middle, that is in the midway between 6 and 7. Now the distance is calculated, so it is 1 dash 2 dash, total distance is 2 lambda. So now unit pattern and the group pattern is multiplied. So the common area again 8 shape, but we have more minor lobes in the resultant pattern. So this is the method of getting the resultant pattern for the radiation pattern of any type of elements according to pattern multiplication technique. So this is one question. The pattern multiplication is the multiplication of single array radiation pattern with 4 options, array factor, beam width, total field, directivity. The answer is the array factor. And the second question, the excitation amplitudes of the binomial array follow Pascal's triangle. Thank you.